Welcome to General Equilibrium on NyQuil Part 3. We're going to be talking about the constraint and the optimization today. So, last time, we ended it on a question of why there would be no savings in period t plus 1 for a two-period model. And the answer is actually fairly simple. It's that there's no period t plus 2. So why would you want to save for a period where you're not going to exist? So essentially, in the final period, you consume everything that you have. So, yeah, you have no incentive because the world ends after period t plus 1. Why would you want to save for a time period where you no longer exist? Now, there are models where you'd want to save for, say, the next generation, but that's a different model. And in this one, literally, like, everything ends. Now, there are infinite horizon models, and one of the advantages of using an infinite horizon model would be that there's no terminal period. And you might be like, well, it's kind of an abstraction from reality because eventually everything's going to end, which is true. Eventually, yes, everything is going to end. However, we don't know when that's going to be. So we're not planning for the end in some particular, like, terminal period. We have no idea when it's going to happen, so we're just going to be planning as if we'll be alive for the foreseeable future. So in this case, there's no st plus 1, but in models with longer time horizons, well, there is. Anyways, let's go with what we think we would get. All right, we would get tomorrow's income, yt plus 1, plus what you saved yesterday, which is savings, plus interest, right? So the amount that you saved times 1, that's what you're getting back, right? Plus the interest rate times what you saved. So you get 1 plus r times s. Now, these two things, tomorrow's income and what you saved yesterday that is paid back to you plus interest today, is what you can consume tomorrow. So tomorrow's constraint actually looks like this. You get yt plus 1 plus 1 plus r times s equals ct plus 1. So if we want to get the two constraints into one, right, because now we've got two separate constraints. We've got a constraint for the first period, a constraint for the second period. What are we going to do? Well, if utilities added together to get lifetime utility, well, what could we do to get a lifetime constraint? Let's write them both out and take a look, right? So equation 2 is the first period constraint. Equation 3 is the second period constraint. Is there anything in there that shows up in both equations? Now, you might think, okay, well, there's y and there's c. Yeah, there is. But the t subscript matters here, right? So yt and yt plus 1 are not the same thing, just like ct and ct plus 1 are not the same thing, right? So while they're both income or consumption, the time period at which they're indexed is going to tell me that they are different values, or they can be different values. They're not required to be the same. But if you look at savings, s sub t, that shows up in equation 2 and it shows up in equation 3. So you can take one of these equations, solve it for s, and then plug that in for s in the other equation. So let's solve equation 3 for s. This is what you get. 1 over 1 plus the interest rate times consumption minus income. And we're going to substitute that into equation 2 to get this right here, where everything in the parentheses is st. So if you look over here, right, y equals c plus s. Well, y equals c plus s. So this stuff right here is what got plugged in here to give me equation 5. We can also rewrite it as this, if you prefer to have the 1 over 1 plus r just be expressed as 1 plus r to the negative 1 because they're equivalent. I like it this way because it's all just like one line. Much simpler. It's a lot less like, oh my God, I got all this math. It's a little bit easier to just kind of read everything across in one line rather than have to worry about two. So if I want to maximize utility subject to a budget constraint, right, meaning I find the maximum of the utility function, but remember there's no maximum of the natural log of x because the natural log function is increasing everywhere. So the better question is, the better way to put it is, what's the maximum when it's constrained at a point that is given by my budget constraint? So I set this problem up. Really, I can do it any number of ways. The best way to do it here is just to substitute the constraint into the objective function, which is the utility function. So I'm going to solve the constraint for CT plus 1, so I have it in terms of CT. And you'll see why in a second, because it actually works out to our advantage to do it this way. Right? So by solving it for CT plus 1, I get 1 plus the interest rate times income minus consumption plus tomorrow's income. And I'm going to plug this into CT plus 1 in lifetime utility. So now the whole thing is in terms of only CT, not CT and CT plus 1. Right? Because if what I have in the parentheses here is equal to CT plus 1, well, I plug this stuff in instead, and now tomorrow's consumption is actually a function of today's consumption. And I've got today's consumption here. So when I take a derivative of this with respect to CT, I can differentiate both terms in this utility function. So I'll take my derivative, but I only need to take one derivative now. It's with respect to CT. So, okay, maybe according to this, I kind of gave away the answer immediately. But yeah, we are taking the derivative with respect to our choice variable, which is consumption. So I want to maximize this with respect to CT. So I get my partial derivative, that partial u of CT over partial CT, and I set that equal to 0. And that's how we're going to get the maximum of a function. Remember, if you take the derivative of a function and set it equal to 0, you're getting either the maximum or the minimum. Now, typically, you would have to check your second order conditions to ensure that you're getting either a maximum or a minimum, but here what I'm telling you is you don't really need to worry about that because I'm promising you that you will be getting a maximum. So from this, I differentiate across the whole thing with respect to CT, and I hold everything else constant. So R doesn't change, beta doesn't change, Y doesn't change. It's just C that I'm allowing to change. Everything else is held constant. So let's go piece by piece. So the first part is easy. The natural log of CT, the derivative of that is going to be 1 over CT. Now the second part needs a little bit of finesse. We need to use something called the chain rule. Maybe you remember that from Calc 1. It's the derivative of the outside times the inside times the derivative of the inside. So the derivative of the outside is this. 1 over everything that was in those parentheses. 1 over 1 plus r times y minus c plus yt plus 1. Then I need to multiply that by the derivative of the inside, which is negative beta times 1 plus r. So the derivative of that second part is this right here. Now, fortunately for us, what I have in those parentheses in the denominator is just CT plus 1. So you can substitute CT plus 1 back in there, and you get negative 1 over CT plus 1 times beta times 1 plus the interest rate. So I add these two parts together, and this is what I get. This is my derivative, 1 over C, or 1 over CT, minus beta times 1 plus R times 1 over CT plus 1. And there's a very, very nice intuitive understanding of this once we set it equal to 0 to get the maximum. So I set this guy equal to 0. So now I have maximized my utility, and I want to solve for CT. So from this right here, I can get 1 over CT equals beta times 1 plus R times 1 over CT plus 1. Or if I want to keep the functional form abstract, I can write it as the marginal utility of today's consumption equals beta times 1 plus R times the marginal utility of tomorrow's consumption. Now, this right here is called the Euler equation, and it relates marginal utility, the marginal utility of today's consumption with the marginal utility of tomorrow's consumption. The marginal utility of tomorrow's consumption is weighted by your personal preferences beta and the conditions of the market 1 plus the interest rate. So you can kind of think of that beta times 1 plus R as like your conscience. All right, maybe you remember like those old cartoons when we were kids, and there's always some cartoon character thinking of doing something really bad, and there's the angel that pops up on one shoulder and the demon on the other. And the angel's like, hey, you should do the really good thing because it's like the good thing to do. And the demon's like, nah, screw that, man, do the bad thing. Well, the right-hand side of this equation is the angel, right? The idea is that your angel, if you were to really boil down a lot of what happened in those cartoons, the angel and demon were just your time preferences. The angel was saying, hey, don't necessarily take the easy way out. It'll pay off in the long run. Whereas the demon is like, nah, screw the long run. Short run gains, long run costs. Who cares what happens in the long run? The short run is what really matters. So the angel's telling you not to consume quite so much today so that you can consume more tomorrow. The incentive to do so is 1 plus the interest rate, right? That interest rate is really your incentive to save. Right, the left-hand side, it says right-hand side here, but it should be left-hand side, is the actual demon. That left-hand side is telling you to consume more today, and the way it's speaking to you is through that beta term. Right, so if we were to rewrite the Euler equation, we can just remember that beta equals 1 over 1 plus rho. So if I write that out like this, okay, this is a little bit easier to understand. The numerator on the right-hand side is the condition of the market, and that is my incentive to save, that interest rate, right? A higher interest rate, the more likely you're going to be to save. That denominator, on the other hand, is my incentive to not save because it's how impatient I am, right? Rho is a measure of how impatient you are. The larger rho gets, the more impatient you get. So if the interest rate is greater than rho, you have an incentive to save. If the interest rate is less than rho, you don't have an incentive to save. So the numerator describes the market conditions. The denominator describes your time preferences. And as I said, because fractions, if the numerator is larger than the denominator, the market's rewarding savings more than your desire to consume today, and you'll end up wanting to save more to consume tomorrow. You can think of it like a penny saved is a penny earned. If the denominator is larger, then you've got rho being greater than r. Your time preferences are greater than the market is rewarding for your savings. You'll want to consume more than your savings. So there's just not much of an incentive to save at this point. So let's graph this guy out really quick, right? You've seen this graph already. We've got our indifference curve. We've got CT plus 1 on the vertical axis and CT on the horizontal. This is my budget constraint. And the budget constraint has a slope of -1 plus the interest rate, right? And at the point where the budget constraint touches the indifference curve at only one point, it's a point of tangency, right? That point right there is given by the Euler equation. So the Euler equation is giving me that point of tangency with the indifference curve and the budget constraint. So it's telling me what my optimal consumption path is, what my optimal consumption is for today and my optimal consumption for tomorrow. And because it's optimal consumption today and the optimal consumption tomorrow, I'm getting an optimal consumption path over the lifetime of my utility function. So the tangent line, which is the budget constraint, has a slope of -1 plus the interest rate. And it touches that utility function at a point where the Euler equation holds. So it's giving me that point of tangency where CT star and CT plus 1 star are points that satisfy the Euler equation. Now, if you were to change the interest rate, what would happen? Well, you would be changing the slope of that budget constraint, right? Say you increase the interest rate. You'll want to consume less today, and you'll want to consume more tomorrow. If we wanted to keep consuming as much today with a higher interest rate, we're losing out on too much. We're losing out on lifetime utility. So if we give up some consumption today to be able to consume more tomorrow instead, lifetime utility becomes maximized. So this would be a different interest rate, right? We've got a steeper slope. So what's going on? Well, it becomes more valuable to us to consume more tomorrow and less today. So I'll call this CT prime and CT plus 1 prime. And if you were to change that interest rate, it would be reflected in the Euler equation, which would give me new values for CT and CT plus 1. Now, if the economy were in a steady state, right, where everything is just moving at the same pace, then rho would be equal to the interest rate. That's for a different lecture, but what's important right now is that you know how to derive the Euler equation and what it means. Now, a nice thing is that general form, u prime of CT equals 1 plus the interest rate over 1 plus rho times u prime of CT plus 1 is always going to be the same. So if you get a different looking utility function, well, all you need to do is get the first derivative of it for today and the first derivative of it for tomorrow, and then you're good. It's literally all that you need to do. Now, the different utility functions aren't going to be an issue in this course. It's only going to be log utility. But if you ever are confused, at least for the Euler equation for consumption, right, because there will be different Euler equations that we get. But the Euler equation for consumption will always be something that looks like this. So if you ever are a little confused, you can just get the marginal utilities, plug that in for u prime of CT and u prime of CT plus 1. Almost always. We'll be explaining in the next lecture why it may not always be that, but under various assumptions of the way the market is operating, it will reduce to something like this. Because, well, okay, I'm getting a little ahead of myself. Whatever. The interest rate is equal to the marginal product of capital. So if we are dealing with a system where there is no interest rate per se, but we have a marginal product of capital, 1 plus the marginal product of capital is equivalent to 1 plus the interest rate. So it may look a little different, but in terms of what you are getting out of this, what information is being provided from the Euler equation, is never going to change. So to wrap up, we learned about utility maximization. We learned how to maximize it for two-period problem. It generates the Euler equation, which tells us about the behavior rewarding the growth rate of consumption. Now, the next time we meet, we're going to talk about the firm's role in this and how we can endogenize output. That's where the stuff gets really, really cool, and that's where we go from just kind of like a dynamic optimization to like an actual dynamic general equilibrium. And from there, we can add money, and you can actually see how monetary policy is affecting various equilibria within the economy, thus how it's affecting the general equilibrium. So all that is for the next couple of lectures. Stay tuned. And in the meantime, practice deriving the Euler equation. That's actually going to be a very important thing for you to do. Practice deriving, well, let's see, where were we here? Practice deriving equation 15. Because the more you do it, the more you work on it, the easier it's going to get. The first few times I had to do it, I was a little confused. I was like, I don't even really know what we're doing. But the more I ground it out, the more I worked on it, the more I began to actually get an intuitive understanding of it, to the point that it's really the only way that I can actually do macro these days. So keep at it. I promise it's a rewarding thing to be able to get. So in the meantime, work on that. Enjoy your weekend, and there will be more lectures coming soon. Thank you for watching.